Hello students, in today's electromagnetic fields lecture, we are going to do the Stoke's theorem first, and just let's start with its definition, that what is Stoke's theorem. So it states that the surface integral of the curl of a vector field A vector taken over any closed surface S. These S and A vector are just the symbols that we are going to use in this proof. Okay, taken over any surface S is equal to the line integral of A vector, that is the same A vector, around the closed curve bounding the surface S. Okay, and mathematically, as you seen from the definition, that on the left hand side there is the surface integral of the curl of a vector field. So mathematically it can be written as curl and its surface integral. Okay, and on the right hand side, there is the line integral of A vector around the closed curve bounding the surface. Okay, so on the left hand side there is the surface integral of the curl of the vector, and on the right hand side there is the line integral of that particular vector. So as you seen here from the formula, it's very clear about its application, that Stokes theorem is used where we have to convert the surface integral into the line integral and line integral into the surface integral. Okay, so that is the main application for the Stokes theorem. As in the last lecture, we have covered the Gauss divergence theorem also. And what is there in the Gauss divergence theorem? That theorem is used to convert the surface integral into the volume integral. And instead of curl, in the Gauss divergence theorem, there is the divergence. Okay, and in the Stokes theorem, here it is the curl. So what is the relation here? That in the case of Stokes theorem, or what is the, you say, the difference, in the case of Stokes theorem, surface is converted into line and vice versa, and the curl operation is used in this theorem. Whereas in the Gauss divergence theorem, surface integral is converted into the volume integral and vice versa, and divergence operator is used. Okay, so this is the statement for the Stokes theorem. Okay, now let's start with the proof part. So, and its proof is almost similar as we have done in the Gauss divergence theorem. So here in this theorem, consider any surface S that is bounded by the curve or bounded by the line L. Okay, so just I'm going to draw any shape of the surface. Okay, here is the surface and here is my line that surrounds this surface. Okay, and what is my vector symbol? That is A vector coming out from this surface. That is the any A vector is there. So starting with the same concept, so consider S, surface S with a line L is its boundary. Therefore, the line integral of A vector, in the first step, line integral of A vector. So simply write it as A dl, and here it is L. So this is the line integral, and we have to proceed in this proof also in the same steps. Like there is firstly the single surface is there. Then in the next step, we divide this surface into two parts. Okay, then in further steps, we divide this surface into the n number of parts in the same way as we have done in the Gauss divergence theorem. Okay, so this is our first step, that is the line integral of A vector is A vector dot dl and line integral. Now divide the surface S into two parts, S1 and S2. So for the next figure, so this is my same surface, and now I am going to divide this surface into two parts. Let us suppose like this. This is my S1 part and here is the S2. Okay, and surrounded by the lines, let us suppose the S1 is surrounded by L1 and this S2 is surrounded by L2. Okay, and this one is the shared portion between S1 and S2. Okay, this is the shared portion between S1 and S2. Now write down in the similar steps. Now the line integral of A vector for surface S1. ठीक है, line integral of A vector for surface S1, that is, it can be written as A dl1 and here it is L1. Okay, and similarly, line integral of A vector for surface S2. Okay, for this portion, so it can be written as A vector dot dl2 and here it is L2. Okay, now as the common line, this one, let us say this line LM. Okay, now as line LM, this one, line LM is common between S1 and S2. See here in the diagram, line LM is common between S1 and S2. Therefore, the line integral of A vector along LM is equal and opposite and cancel out each other. Okay, so the line integral across LM for S1 and S2, okay, it is equal and opposite and therefore they are cancel out each other. Hence, common. Hence, their line integrals cancel out each other. Okay, now what is the net line integral? जैसे हमने last divergence theorem में we then finally calculate the net flux diverging. Okay, so the net line integral so this comes out to be, this is equal to this one, that is A dl, it is equal to A vector dl1 and here it is L1 plus A vector dl2 and here it is L2. Okay, so this is the net concept when the surface is divided into two parts. Now, what is the next step? Now we have to divide the surface into n number of parts. Okay. So in the next step, now we are going to dividing the surface S into n number of parts. That means S1, S2 up to Sn, and these surfaces are surrounded by the lines L1, L2 up to Ln. Okay, so in the similar way, so it can be written like this. So as it is written here, so in the similar way, it can be written as, that is A vector dot dl, and here it is the line integral, it is equal to A vector dl1 L1 plus A vector dl2 L2 plus and so on, that is A vector dln and here it is Ln. Okay, and in the summation form, so this can be written as summation of I is equals to 1 to n of A vector dl I, and here it is also Li. Okay, so in the summation form, it can be written like this. Okay, now proceeding with the same step. So what after this in the Gauss divergence? There we divide the numerator, or we multiply and divide by the volume in the Gauss divergence theorem. But here, instead of volume, we are using here the surface. Okay, so in the next step, multiply and divide by the surface S. Okay, or you say here ki multiply and divide by Si, because here we are going to convert this into the summation form. So this comes out to be A dot dl L, this one, just write it in the same manner, and equal to summation of I is equals to 1 to n Si A dli, here it is Li, divided by again Si. That is, we multiply and divide that relation by Si. And mark it as equation number 1 now. Okay. Now, as you seen here that when the surface is a single surface, so it is a of large area. But when we divide the surface into two parts, the area reduces. Okay. And similarly, if we divide the surface into the n number of parts, so n may be 20, 30, 200, 500, maybe a large number of parts. So as the number of parts are more, the surface area going to be reduces. Okay, so what does this mean? That in the next step, we have to take the limit that if n is large, that means if n is large, what is n? N is the number of parts that we are going to divide the surface. Okay, if n is large, so that means then S is small. Okay, the area of that particular surface reduces. So what does we mean? That mathematically we represent it like this. If n tends to infinity, then Si tends to 0. Okay, as the number of parts are increasing, the surface area going to be decreasing. Okay, if n tends to infinity, Si tends to be 0. Okay, now there is one formula of limit that we are going to apply here. It is the limit of this portion. Okay, therefore, limit of Si tends to 0 for this portion, that is A dli, that is a line integral of A vector divided by Si, and this formula represents your curl operation. Okay, this formula represents your curl operation. That means this is equal to del cross A vector. Okay, and mark it as equation number 2 now. Now in the next step, just convert this summation sign, this pending summation sign, into the integration. Okay, so this one is equal to also summation of I is equals to 1 to n of Si is equal to the surface integral ds. Okay, mark this as equation number 3. Okay, now in the next step, put 2 and 3 in 1. Okay, just put 2 and 3 here in 1. Okay, that means put 2 and 3 in 1. So this will gives you what is the equation number 1. On the left hand side it is a vector dot dl, that is the line integral of a vector, it is equal to, now this becomes your surface integral and this becomes your del cross A. Okay, so this is the surface integral of del cross A, and this is the final proof for Stoke's theorem. Okay. Hence proved. And what is the application of Stoke's theorem? That it is used to convert the line integral into the surface integral and vice versa. Okay, so this is the final proof for the Stoke's theorem. Okay, now let's start with the next theorem, that is the Greens theorem. And for the Greens theorem, a direct proof will start. Okay, and from that proof, some results will be there, and that will be called as the final results for the Greens theorem. So let's start with the Greens theorem. So consider any A vector, consider A vector is equal to psi del phi. Okay, this I have just taken the symbols. Okay, and we know the del is the nabla, is a vector quantity, and here what we have done is the gradient, and gradient of any scalar is again a vector quantity. Okay, so and where this symbol is called as psi and this symbol is called as phi. Okay, where psi and phi are scalars. Okay, where psi and phi are scalars, and as you have seen here that this one is the gradient, this one is the gradient of any scalar, and we know that ki gradient is a vector quantity. Okay, what is gradient? It is a vector quantity, and when this vector is multiplied by any other scalar, so what is the result? Result is again a vector quantity. So I'm written here any vector A vector. So any vector A vector can be written like this. Okay, by using the combination of scalars with del. Okay, so I'm going to write here A vector is equal to psi del phi, where del phi is the gradient which comes out to be a vector quantity. Okay, so this is psi A vector is equals to psi del phi. Now take the divergence of this equation. Take divergence. That is del dot A vector on the left hand side. Del dot A vector is equal to del dot psi del phi. Okay, and now just solve it like as we have done in the case of differentiation. Like if there are two terms, so we take the differentiation of first, keep the second as constant, and then do the differentiation of second, keep the first as constant. So in the similar way, we are going to do the differentiation here. So it can be like firstly do the differentiation of this first. One term is this and other term is this. Okay, so it can be written as del psi del phi. This second I cannot change. It can be written as it is del phi. Okay, and in this step, I am taken the gradient with psi plus अभी इसको first को as it is रहने देना है, that is psi, and multiply it with the second term. So it comes out to be del square phi. Okay, so this is the formula. When we do the divergence for this psi del phi, so this is the formula. Okay, and what is this operator? Del square. So it is generally called as the Laplacian operator. Okay, this one is called as Laplacian operator. Actually, this comes in our further topics. So this one is called as Laplacian operator. Okay, and this one will act as like the double differentiation of any scalar or vector. Okay, so this is the result, that is for del dot a vector. Now in the next step, put the value of del dot a vector and a vector in the divergence theorem, in the Gauss divergence theorem. So in the next step, or first of all, I am going to write down here the Gauss divergence theorem first. Now, as Gauss divergence theorem is, that is which represents the relation between the surface integral and the volume integral. So the Gauss divergence theorem is here, it is del dot a vector dv, volume integral of the divergence of any vector field, it is equal to the surface integral of the same vector. This is my Gauss divergence theorem. And now just put down the value of a vector and del dot a vector in this. Or I'm just going to mark it as equation number 1, this as equation number 2, and this as equation number 3. So that means put 1 and 2 in 3. Put 1 and 2 in 3. So it comes out to be, that is the volume integral of del dot a. This one is our del dot a. That is del psi del phi plus psi del square phi dv. Okay, here I am going to put down the del dot a here, and it is equal to a ds, that is the surface integral of a vector is my psi del phi ds. Okay, so this one is, the final result, and it is called as the first form of Green's theorem. Okay, this is our final result, and this is called as first form of Green's theorem. Okay, this is called as first form of Green's theorem. Now there is one more form of Green's theorem, and for that just interchange psi and phi. Okay, from this mark it as equation number 4. Now in the next step, in equation number 4, interchange psi and phi. Okay, the scalars that we are assumed in the starting, just interchange their positions. That is, with the gradient there comes out to be now psi, and outside the gradient there comes out to be the phi. Okay, so it, and rewrite this equation number 4. So equation number 4 can again be written as, that is the volume integral of del. Now here it is psi, and I am going to write it here as phi. Okay, I'm just going to interchange the position of psi and phi. So it comes out to be del phi del psi plus phi del square psi, like this. I am interchanging their positions. Okay. And there is now the volume integral dv, and it is equal to phi del psi ds, surface integral, after interchanging the positions of psi and phi. Okay, mark it as equation number 5. Now in the next step, subtracting phi 5, equation number 5 from equation number 4. Okay, like subtract in the next step, subtract 5 from 4. So this is our next and final step. Just subtract 5 from 4. And when you are going to subtract them, na, so don't mix the left hand sides and right hand sides. Just put down the statement on the left side and right on the right side. Okay, so this one is the same component, del phi del psi. It is del psi del phi. So it cancel out each other. Okay, and so here comes out to be the volume integral of psi del square phi minus this term phi del square psi dv is equal to the surface integral of psi del phi minus phi del psi ds. Okay, so this is the second form of Green's theorem. Okay, so these are the results for the Green's theorem, and this is also used in our further concepts when we are going to actually deal with the electric and magnetic fields. Then we are going to use these theorems directly, these results directly. Okay, so this one is called as, second form of Green's theorem. Okay, so this is called as second form of Green's theorem. Okay, so let's start with the next theorem, that is the Helmholtz theorem. Actually, this theorem, the name of this theorem is upon its scientist name Helmholtz, and it states that a vector field is completely specified by its divergence and curl. That means any single vector field is specified by the sum of its divergence and curl. Okay, and secondly, it has another definition, like any vector field may be expressed as the sum of an irrotational vector and a solenoidal vector. And we know that what is irrotational vector whose curl is 0, and solenoidal vector whose divergence is 0. Okay, so any vector field, let us suppose any A vector, so that A vector is completely specified by the sum of its curl and divergence, or it is del cross A plus del dot, any vector. Okay, that is specified by the irrotational vector and a solenoidal vector. Solenoidal vector whose divergence is 0 and irrotational vector whose curl is 0. So let's start with the proof now. Now, as written in the statement, that a vector field is represented by its curl and divergence. Any single vector field is represented by its curl and divergence. But here in the proof, we have taken to assume, we starting moving opposite to this statement. Like there is not a single vector that is represented by the same divergence and curl, but we assume that there are two vectors showing the similar results for the divergence and curl. Okay, so let's start with the proof from this concept and just write down here that let's assume opposite to the above statement. So let's assume opposite, or you can say contrary. Let's assume opposite to the above statement. Above statement that there exist two vectors. There exist two vectors, say F vector and G vector. Say F vector and G vector, any two vectors showing the similar results, showing similar results for divergence and curl. Okay, so we start our proof with this assumption that there are two vectors, F vector and G vector, showing similar results for divergence and curl. So these two vectors, if they are showing the similar results, then they must satisfy the same boundary condition on any surface S. Okay, if they are showing similar results, then they must satisfy the same boundary condition for any surface S. And for satisfying this boundary condition, so mathematically it can be written as F vector, therefore F vector into any unit vector, let us suppose A, that is must be equal to G vector dot, okay? So that means showing similar results on boundary also. Okay, showing similar results on boundary also. So this be our first condition, and it can be now written as F vector minus G vector an, this is our unit vector, okay, is equal to 0, and mark it as equation number 1. And we have also said that both show the same divergence, same curl. So it can be written like this also: del dot F is equal to del dot G. Okay, we are assumed this as here. So it can further be written as del dot, here it is dot, F minus G is equal to 0. Mark it as equation number 2, and del cross F vector is equal to del cross G vector, and this is can be written as del cross F minus G vector is equal to 0. Mark it as equation number 3. Okay, and now from 2 and 3, from equation number 2 and 3, so what is seen here that F is any vector, G is any vector that we have assumed, and what is the result of vector minus vector? So it is again a vector. Okay, so as from the equations 2 and 3, it has seen that the F minus G, let us suppose H. So from 2 and 3, as F minus G is again any vector h. Okay, because vector subtracting the vector result is a vector. Okay, any vector h is both. देखो, if f minus g is h, then del dot h is equals to 0. So that means that this h vector is a solenoid. Okay, and from this condition, it is concluded that the h vector is irrotational also. Okay, so f minus g that is equal to h vector is both solenoidal and irrotational. Okay, as seen from the equation number 2 and 3. So therefore, any irrotational vector can be written as the gradient of any scalar field. This we have done in the identity. Okay, any irrotation vector, therefore, any irrotational vector, it is equal to the gradient of any scalar. It can be represented like this. Any irrotational vector, it is equal to the gradient of any scalar field. So it can be now further, in the further steps, so therefore the h vector can be written as gradient of any scalar. Okay, and we are going to take that scalar as phi, and therefore let h vector is equal to del phi. That means h vector is our irrotational vector, and that is equals to del phi. That is the gradient of any scalar quantity. Now, or you can also write, mark it as equation number 4, or also write it as f minus g vector is equal to del phi. Mark it as equation number 5. Okay, now put 5 in 2. In the next step, put 5 in 2. So put down this 5 in equation number 2 here. Okay, instead of f minus g, just write down del phi. It comes out to be del dot del phi is equals to 0 as per our equation number 2, this one. Okay, so it comes out to be, further it can be written as del square phi is equal to 0, and this del square, I am again repeating, this is called as the Laplacian operator. Del square is called as Laplacian operator. Now from the first form of Greens theorem, now I am going to use here the first form of Greens theorem. Now from first form of Greens theorem, I'm just going to write down here the complete first form of Greens theorem. That is, the on the left hand side it is the volume integral, and it one is psi del square phi minus phi del square psi dv is equal to the surface integral on the other side. Okay, surface integral of, no, actually this one is the second form, and here it is psi del square phi plus del psi del phi and this is equal to psi del phi ds. This is our first form of Green's theorem. Now, for a special case, in this first form of Green's theorem, taking special case when phi is equal to psi or psi is equal to phi. Taking a special case of psi equal to phi. That means put down here psi equal to phi. Okay, and I'm again rewriting the Greens theorem now. So here it is the volume integral, and this comes out to be phi del square phi and del phi into del phi. So here it is phi del square phi plus del phi. So it comes out to be del phi square. Okay, and dv. And on the other side, it can be the surface integral, this one, s phi del phi ds. Okay, this is after considering the special case in the first form of Green's theorem. And as seen from here, this concept that del square phi is equals to 0. Okay, del square phi is equals to 0. So that means here this component is equal to 0. So we are left with this one and this. So this comes out to be volume integral of del phi whole square dv. It is equal to the surface integral of phi del phi ds. Okay, what is the reason? Because del square phi is equal to 0. This is the reason for this equation. Okay, now mark it as equation number 6. Mark this as equation number 6. Now using equation number 4 and rewriting the equation number 6. Okay, using equation number 4, therefore the right hand side of 6 can be written as this right hand side of equation number 6. It can be written as the surface integral of phi h vector ds. So this can be written like this, and on the boundary condition, so this is equal to, if I'm going to write down it on the boundary condition, it can be written as h vector with its boundary unit vector ds, and this is equal to 0, because this concept is from the equation number 1, because for the equation number 1 f minus g into an unit vector is equal to 0. So from that equation number 1, this is equal to 0, because from equation number 1, that is taken from the equation number 1. Now the left hand side of equation number 6, LHS of 6. This is our equation number 6, and this is our left hand side. So I'm going to write down it here. That is V volume integral of del phi dv. And what is del phi? That is the h vector from equation number 4, and this can be written as volume integral of h vector square dv, and this is equal to 0. Now why it is 0? Because for the equation number 6, we have recently proved that this left hand side is 0, because the left hand side, because RHS of 6 is equal to 0. Okay, that's why the left hand side is also equals to 0. And this is possible only if h is equals to 0 everywhere in the volume. Okay, that means when this condition is possible, or when this h square, the volume integral of h square is equals to 0. So this is possible. This is possible when h vector is equal to 0 everywhere in volume V. Okay, this is possible only when h vector is equal to 0 in the volume V. So if h vector is equals to 0, so that means therefore f minus g vector is equal to 0 everywhere in the volume V. And if f minus g vector is equal to 0 everywhere in the volume V, so this can further be written as, that means f vector is equal to g vector. See, okay. So what does we observe from all this study? That there are no two separate vectors that show the identical results. So that means both the two vectors are the same vectors. They are not the separate vectors. The f vector and g vector are equal everywhere. They are showing the identical results. Okay, so this is the main concept. So hence, thus no two vectors can show the identical divergence and curl everywhere. So it means that no two vectors show identical results for divergence and curl. That is, for the same divergence and same curl, both the two vectors will be same. Okay. And hence from this we have observed that from equation number 3, now the final result. Now from third, del cross del phi is equal to 0. So from this equation number 3, del cross del phi, so what does this mean? So this means that the gradient of a scalar field, okay, this is the gradient of a scalar field is a irrotational vector. Okay, so this means that the gradient of, just write down here, okay, gradient of scalar field is irrotational vector. Okay, gradient of scalar field is irrotational vector. This is our one of the identity also. And also from equation number 2, so it is observed that from 2, del dot del phi is equals to 0. So what is this mean? That this means that that means the curl of a vector field is a solenoidal vector. That means, and from here we have also written here that del cross curl of a solenoidal vector. This is also one of our identity. So this is the curl of a solenoidal vector is 0. The curl of a vector field is a solenoidal vector. So it can be written like del dot del cross A vector. It can be written like this. That is, the curl of a vector field is a solenoidal vector. Hence, in journal, the vector can be represented as, so in general, a vector field can be represented as the sum of the irrotational vector and a solenoidal vector. Okay, so the vector field can be written as, therefore, vector field can be written as any vector field F, that is the sum of solenoidal vector and irrotational vector. Okay, and in this representation, this is your solenoidal vector. This is solenoidal vector, and this one is irrotational vector. Okay, del phi is irrotational vector, from where this is concluded that it is irrotational vector from this equation. Okay, del phi is irrotational vector whose curl is 0. Del cross A is solenoidal vector whose divergence is 0. Okay, so that's why a vector field can be completely represented by its solenoidal vector, sum of the solenoidal vector and the irrotational vector, or the vector field is completely specified by the divergence and curl. Okay, so this is all about the Helmholtz theorem. Okay, so what it generates that there is a single vector which shows the similar results for divergence and curl, and also the vector field is represented by the sum of the irrotational and solenoidal vectors. Okay, so what we have done in today's lecture, one is the Stoke's theorem, another one Greens theorem, and finally this Helmholtz theorem. Okay, so thank you for this lecture.